Hello everyone, welcome to this video. In this video we shall be looking at the answer to this question, which the question here is, what is the number of conjugates of the element A? So here we have a result regarding this. The result tells us that if G is given to be some finite group, so you see finiteness is necessary here. Why? Because you'll see that in the proof of this result why finiteness is required. So if we are given some finite group and if A is some element of the group G, then the number of elements which are present in the conjugacy class of A, that is equal to the index of the centralizer of A. What is C of A? If you remember, it represents the centralizer of some element A, right? And this element A is present in G, and centralizer contain all such elements. It is a set of all such elements which commute with A, right? And centralizer becomes the group whenever we have G as an abelian group. So with these properties here, it is this result tells us that for a finite group and for an element A, we have the conjugacy class of A. Conjugacy class contain all the conjugates of A. And what are the conjugates of A? We will call B as the conjugate of A. If we are able to write it as X A X inverse, where what is X? X is any member from the given group G, right? So here that means we are to show that the number of conjugates for this element A is equal to the index of the centralizer of A, correct? Okay, now in order to prove this result, what we are required to prove? We are required to prove that the order of the conjugacy class of A is equal to the index of G in index of the centralizer of A, where what is A? A is some element in G, right? For that, what do? We define some function T such that T is a well-to-well mapping. It is one-to-one and it is on-to, and we define T such that we connect both of them. If both of them, they are connected by T, and they would then have the same number of elements if all the elements here is mapped to exactly the same number of elements here, and that is proved by proving a bijection. So what we do, we consider a mapping which takes all the elements here from the conjugacy class to the cosets or vice versa, and then we prove that the mapping is one-to-one, it is on-to, and it is well defined. If that is there, then the number of elements would be the same, and if they are same, so that means the number of elements would be the same. So for that, we define some mapping which we are calling by T, such that all the elements of the left coset X C of A are mapped to the conjugates of A, which is X A X inverse. So you see this X and this X is the same, and what is X? X is taken from the group itself, right? So the mapping here is T of XCA. What is capital C of A? It is the centralizer of A. So X multiplied with the centralizer of A, and what is it? You know, the centralizer of A, that is a subgroup of the given group G. If this is a subgroup, so we can create a coset out of it. So what we can do, we can have some element X from G such that X into the centralizer of A, this is equal to the left coset of G, right, of this subgroup C of A, which is generated by the coset representative X, right? So we are mapping XCA into the conjugate of A. Now in order to prove that T is a well-defined mapping, it is one-to-one and it is on-to, let's proceed by taking two elements X and Y from G. So if we take two elements X and Y from G, right, and we know that so if we suppose that XCA is equal to YCA, now because in order to prove a well-defined mapping, what do we do? Now what is your T? T was XC of A, this was equal to X A X inverse. Now in order to prove that the mapping is well defined, what do? We take the domain elements as equal. So we take two different elements X and Y, so that X C of A is equal to Y C of A, and we will prove that their images, that is T X C of A and T, Y, C of A are equal to each other for well-definedness. Next, in order to prove the one-to-one case, what do? We take the two different images as equal, and we prove that the domain element X C of A and Y C of A, they are also equal to each other. So here the steps are if and only if case. So we start by considering X C of A for well-definedness. We consider the domain elements as equal, so we assume X C of A is equal to Y C of A. If that is so, then according to the properties of this centralizer, we have Y inverse X is a member of centralizer of A. If Y inverse X is a member of the centralizer of A, so that means this would commute with A, because centralizer contain all those elements which commute with A. So therefore Y inverse X of A would be equal to A Y inverse of X, right? We have this expression according to the definition of centralizer of A. Now next, what we can do, we can pre-multiply on both sides with Y, so that here you would have Y, here also you would have Y. So here Y into Y inverse would become the identity. So we have E here, and here we have this expression as whole, right? Next, what do we do here? We wanted to have X inverse here, so we post multiply by X inverse on both sides, so that this term would become the identity. So we have identity here, and here we have XA X inverse, so that you have XA X inverse is equal to YA Y inverse. And if you see, what is it? It is nothing but the image of X C of A. So here XA X inverse is the image of it is the image of XC of A, and YA Y inverse is the image of YC of A, correct? So this is for the well-defined part. Now for the onto part, we assume this thing that these two images are equal to each other. If these two images are equal to each other, we can apply the definition of T to obtain these two terms. If these two terms, they are equal to each other, so that means we can again post multiply by X on both sides, so that these terms become identity. We have this expression, correct? Now what we can do, we can pre-multiply both sides by Y inverse, so that this term becomes identity, and we would have this expression over here, right? Y inverse X of A Y inverse of X, right? From here you can see Y inverse X commutes with A, so therefore it belongs to the centralizer of A. So Y inverse X is a member of the centralizer of A. If it is a member of centralizer of A, so that means X into centralizer of A is equal to Y centralizer of A according to the properties of centralizer, and hence we have proved the one-to-one part also. For onto, what do we require? We require that for each of the image element, we have some element present in the domain. So for every X which is a member of G, and for every image element, what is the image? The conjugate of A. So XA X inverse. For every XA X inverse, we have a coset X. Why? Because for this we require some element X from G, right? And whenever we have some element X from G, we can use it to construct the coset of A. So therefore this element would definitely be there, right? So therefore this is onto. Now because we have proved our given mapping to be well-defined, one-to-one and onto, so this would give us the number of conjugates of A which are XA X inverse equal to, so this number is equal to the left cosets of G, right? So we have this thing over here. And what does it mean? What is this order? XC of A. We can also express it like this: G colon and then C of A. So it is nothing but the index of A. This thing is known to us according to the Lagrange's theorem. So this order is equal to this order, so hence we have our result. So I hope you understood this theorem well. Well, that is it for this video. Thank you for watching.